All right, today we're going to peel back the curtain on something that affects pretty much all of our wireless tech, from your Wi Fi router to that 5G signal on your phone. We're talking about RF impairments. This is the hidden, unavoidable static, the glitches that engineers are in a constant battle with. So let's get right into it. So let's just start with a really basic question. I mean, with all the incredible technology we have, why isn't our wireless stuff just perfect, you know? Why do calls still drop? Why does your data slow down? Well, on paper, in a perfect world, it should be flawless. But as you can probably guess, reality is a whole lot messier. And this, right here, really gets to the heart of the problem. Over on the left, you've got the textbook ideal, a perfect, clean wave carrying pure information, no errors, no nothing. But on the right, well, that's the real world. It's a noisy, distorted, messy signal. And all that corruption, that's exactly what we're talking about today. So let's put a name to it. These distortions are called RF impairments. And what's really important to get is that these are not software bugs or simple glitches you can patch. Nope. They are unavoidable side effects of using real physical hardware. Think about it like this. You can't build a car engine that's perfectly silent, right? There's always some hum, some vibration. Well, it's the same idea here. You just can't build a perfectly clean radio. There's always going to be some noise. So what exactly are these little gremlins in the machine? We're about to meet the three main culprits. I kind of like to think of them as a rogues gallery of signal disruptors, and each one has its own special way of causing chaos for our wireless communications. Okay, first up we've got phase noise. Now every single radio has a tiny internal clock. It's called a local oscillator, but just think of it as a super fast metronome that keeps the timing of the signal perfectly precise. Phase noise is what happens when that metronome isn't perfectly steady. It jitters, it wavers just a tiny, tiny bit. And this little instability in timing, it has massive consequences for the signal. And here's the damage report. That little timing jitter doesn't just make the signal wobbly, it actually spreads out the signal's energy into places it shouldn't be. Imagine you're trying to read a sentence, but all the letters are just slightly smeared and blurred together. That's exactly what phase noise does to our data, causing different channels to bleed into each other. Our next troublemaker is called IQ imbalance. Now, to squeeze more data into a signal, modern radios do something really clever. They build the signal from two separate parts, the I and Q components. You can think of them like two waves that have to be perfectly synchronized and balanced. But, of course, in real-world hardware, that perfection is almost impossible. One part might be just a little bit stronger or a little bit delayed, and that creates an imbalance. So what's the big deal if these two parts are a little out of sync? Well, first, it warps the shape of the signal itself. But the real problem is that this imbalance actually creates an unwanted mirror image of the signal, like a ghost signal that shows up where it shouldn't be, and it directly interferes with the real data we're trying to get. And our final villain for today is non-linearity. This one mostly rears its ugly head inside the power amplifier. That's the part of the radio that gives the signal its muscle so it can travel a long distance. In a perfect world, an amplifier would be like a perfect photocopier, just making a bigger, identical copy of the signal. But in reality, especially when you crank up the power, it starts to distort things. It adds its own noise into the mix. The main problem this causes is something called spectral regrowth. Now, that's a fancy term, but all it really means is that the signal starts to bleed out into the neighboring channels. As the amplifier tries to make the signal stronger, it also makes it grow into frequency lanes where it absolutely does not belong. And this is a huge deal, because it can create interference for other people on totally different channels nearby. Okay, so we've met the bad guys: phase noise, IQ imbalance, nonlinearity. But why should you actually care about any of this? Well, let's connect these kind of abstract problems to two pieces of tech that many of you know and use: the 5G network in your pocket and software-defined radio, or SDR, which is a huge tool for hobbyists and engineers. And here it is, the main takeaway. For all the incredible speed and power of 5G, it has a secret weakness. It is extremely sensitive to phase noise. In fact, you could argue it's one of the single biggest hardware challenges for engineers who are building out our 5G networks. And here's why it's such a big deal. 5G gets its amazing speed by packing thousands and thousands of tiny little data channels, called subcarriers, incredibly close to each other. It's like having lanes on a highway that are only inches apart. Now, remember how we said phase noise smears the signal? Well, in 5G, even a tiny bit of that smearing is enough to make those tightly packed channels overlap and corrupt each other. The result? More errors and slower data speeds. Literally the exact opposite of what 5G is supposed to deliver. Now let's switch gears and talk about software-defined radio, or SDR. For anyone who's ever tinkered with an SDR, this is all going to sound very, very familiar. See, unlike your phone, which does a great job of hiding all the messy stuff from you, an SDR gives you the raw, unfiltered signal. And that means you see every single one of these hardware imperfections up close and personal. When you're using an SDR, impairments like IQ imbalance aren't just some theory in a textbook. They are right there on your screen, distorting the signal you're trying to work with. So for the whole SDR community, understanding this stuff isn't just academic curiosity. It's an absolutely essential skill for building, for testing, and for debugging any project you're working on. So if these problems are literally baked into the physics of our hardware, does that mean we're just stuck with them? Is it hopeless? Well, not at all, actually. Modern engineering has an incredibly clever weapon to fight back against all this noise. And here is the core strategy, the big idea. If you can't build a perfect radio, you build a smart one. We've basically accepted that the hardware is going to have flaws, so we use incredibly clever software to clean up the mess after the fact. It's the magic of digital signal processing. We're fighting messy, real-world physics with clean, perfect math. So how does this actually work? Well, it's like a three-step dance that happens millions of times every second. First, the system measures the signal that's coming in and figures out exactly how it's been distorted. Then, powerful algorithms calculate the precise anti-distortion, basically the perfect opposite of the impairment it just found. And finally, it applies that correction to the signal, canceling out the noise and hopefully restoring the clean signal we wanted in the first place. So let's just quickly recap the big story here. First, this signal noise, these RF impairments, they're not a choice. They're a fundamental limit of physics and hardware. Second, that noise directly hurts the performance of our most advanced systems, like 5G. And third, our best weapon against it isn't trying to build impossible perfect hardware, but using really, really smart software to clean up the unavoidable mess. And that really leaves us with a pretty fascinating question for the future, doesn't it? As we keep pushing for more, faster speeds, more connections, looking ahead to 6G and technologies we haven't even dreamed of yet, our digital correction techniques are going to have to get even smarter. But are we getting close to a point where the physical noise is just too much for even our best algorithms to overcome? That's the challenge engineers are tackling right now. Thanks for joining me.